Hey folks, we're going to go over a couple common algebraic errors so we don't make these mistakes this year. Let's start off with 3 over a plus 3 over b equals 3 over a plus b. Of course, this is, at the end of the day, is a fraction, and this is a fraction. And so when we add fractions, we need to have common denominators. So we cannot combine these as it is. We need common denominators. So what we can do, 3 over a plus 3 over b would be equal to, my common denominator would be a and b. So I need an a and I need a b from both denominators. This already has the a, so it needs a b, so I'd have to times that 3 by b. I'd have to times this 3 by a. This does simplify in this case, but even from here, I still can't cancel anything because I remember it has to belong to all pieces when it comes to division and addition or subtraction, and nothing belongs to everything. So just a reminder, when you have fractions, you must have a common denominator. The next one is the reverse of this. So I've got a fraction that's together. I can't split this up. I can't separate this with different denominators. I mean, the denominator here is c plus d. It doesn't work when I break it apart. If you think about it, these don't have common denominator. So if I had what I could do, so must separate with a common denominator. So what is legal, a plus b over c plus d, can be rewritten as a over c plus d plus b over c plus d. Now, if you notice then, both of my fractions have the common denominator. So when I add up, I have that common denominator again on the bottom. Okay, order of operations. Now remember, these are some, please excuse my dear Aunt Sally, is probably how you were taught. I teach it a little bit differently. I teach it as a house. So here's a quick review of how I think about the operations. So on the bottom floor of the house, we have addition and subtraction. Next floor up is multiplication and division. Next floor up is exponents and roots. And then in the top is parentheses. So the order of operations work from the top down. Operations work well if they are near each other. So for instance, exponents work well with division. They're one floor apart. Now multiplication and division work really well together because technically they're the same operation from a different perspective. But exponents and addition, or exponents and subtraction, do not work well together, and that's what this is saying here. It's so tempting to write a minus b squared and just square each pieces. That doesn't work like it. They are too far apart. So if I were to try to clean this up, it would look like a minus b squared means a minus b times a minus b, which then I would have to distribute. A times a is a squared, and then minus ab would be minus 2ab, and then plus b squared. That's legal. Now what we did, look what happened there. I took a subtract and exponent problem and turned it into a subtract and multiply problem. Multiply and subtract work well together. They're only one floor apart. So again, if we apply that idea here, roots are the top floor, addition is the bottom floor. I wish this worked the way that it did, but they're too far apart. Roots and addition are too far apart. Let me just prove it to you with an example of actual numbers. Let's do 9 plus 4. If this property worked, I would be able to do this. Well, let's see if these numbers are true. 9 plus 4 is 13. The square root of 9 is 3. The square root of 4 is 2. The square root of 13 is not 2. It just doesn't work. It doesn't work. I wish it did. And the reason it doesn't is because add and roots, my marker is dying, roots and addition are too roots and addition are too far apart in the order of operations. Okay, so here's our next one. We've got some division and we've got some addition. That's good. They're near each other. Addition and division are only one floor apart. And so people look at this and they think of, oh, wait, a fraction on the bottom. I do that move where I flip and multiply. You can't flip and multiply unless it's a division problem. And what I mean by that is a division of two fractions. We've got a division of a 1 divided by, and then these fractions are added together. So I have to combine those first to be able to do the flip and multiply move. So I would have to combine first, then multiply by the reciprocal. So in other words, I could clean this up. Again, my common denominator, similar to the one we did up above, would be AB. So this one needs a B, this one needs an A. So I could rewrite this as 1 over B plus A over AB. And then I could flip and multiply now and bump this thing up to AB over B plus A. And that would leave me with AB over, and I like to put them in alphabetical order, A plus B. So you can clean things up. You can flip and multiply, but they have to be combined into a fraction first. Here we are again. I've got a square root and a squared. Those things work really well together. Exponents and roots are great together, but not when there's a subtract in the middle. The subtract messes this whole thing up. We cannot simplify this because roots and addition, now in this case, sorry, roots and subtraction are too far apart. They don't work well in the order of operations. Again, I could put numbers in there and show you that it doesn't work, but you could test that on your own. All right, so now we've got some exponent errors, some common mistakes that kids do with exponents. There is a difference between these two things. In this case, I've got negative a, and the squared is around everything, and over here we've got negative a squared. There's a difference. Negative a squared means that the negative and the a are getting squared. If you take a negative a and you multiply it by another negative a, you would actually get a positive a squared. This, and we don't usually teach this with negatives, but the way you want to think about negatives is that's really a negative 1 connected by a mult. Negative a squared means negative 1 times a squared. So in this case, this squared gets applied first and then the negative. Where over here, the negative and the a go first because, parentheses, order of operations, that's the strongest operation. So the negative gets applied first and then the squared. That's why you get two different results here. In this case, the negative gets squared. In this case, the negative does not get squared because it's not grouped in. Negative exponents, this is a big one. This is going to happen over and over and over. You're going to see lots and lots of negative exponents. And negative exponents don't mean it goes on the bottom. It means flip. So this negative exponent, it means that this is going to flip to the bottom. So right now, this is a to the negative second over 1. So when it flips, it becomes a to the positive second on the bottom. And a to the negative 2 is actually over 1. And then when you flip it to the bottom, it becomes a positive. That's the same argument if I were to go the other way, 1 over a to the negative 2. Now it's on the bottom. Now it would flip up to the top, and this would be a to the second on the top. So it doesn't just mean it has to be on the bottom. It just means flip. So negative exponents mean flip. So what does this mean? This means the same as what it meant over here. This is a negative number, negative 1 times a squared. This is a negative number. This is a negative coefficient where this is a negative exponent. I mean, think about it. When you first learned about negative numbers in 4th grade or whatever, you weren't flipping things over. So a negative out front is different than a negative in an exponent. A to the 2/3 is equal to a to the second over b to the third. Unfortunately, that's not true either. Fractional exponents mean roots. So what I mean by that, over here, negative exponents mean flip, fractional exponents mean roots. This part, so if I have a to the 2/3, that becomes this. I don't have a great name for this, how to separate. I call it the power, even though technically the whole thing is the power. Maybe I should call that the exponent. I don't know. This is the root. So a to the 2/3 becomes the cube root of a squared. And then over here, a common mistake is who is the exponent connected to? If you look at this problem, this is overall a multiply problem. There is a multiply between the 2 and the a here. This is 2 times a to the -1. Now, we just reviewed that negative exponents mean flip, so this gets turned into the 2 over a to the first, or just a. Now, why didn't the 2 flip? Because the 2 doesn't have a negative exponent. So if you look at over here, the common mistake is people want to flip both of them, but the negative exponent is only actually connected to the a. Common mistake in distributing errors. Distributing works when you have a multiply and an add or subtract combined. So for instance, if I had 3 times x plus 4, I would distribute this 3 to everybody inside. So we would get 3 times x, which is 3x, 3 times 4, which is 12. That doesn't work unless it's add and subtract working with multiply. This is all multiply. Now, kids want to distribute this because they kind of think of it this way. But if I asked you to do 2 times 3 times 4, you would never do 2 times 3 and then 2 times 4. You would do 2 times 3 and get 6 and then times it by 4. And that's what this example is showing. This is not a distribution problem. A times BC is ABC. A times B times C. That's just all multiplied together. Now, with the rest of these, it's all the same argument. It's the same mistake every time. It's how sine, log, tangent, cosine, how these are attached to their group. You would never say that this is connected by multiply. This is called square root of. Here's that of phrase. This is connected by of. This is read sine of 2a. So this is an of, not mult mistake. You can't take this. Now, look at this 2 is connected by mult. This 2 is, but this is not. That 2 and that a are both inside of the sign. So as we move on to the next one, again, it's tempting to distribute here. You feel like it because up to this point, when I write 3x, that means 3 times x. But it doesn't work in the world of logs and sines. You have to think about your trig and log things as being like a square root, as being around the function. So this is of, not mult. So remember, we would clean this up. I don't know if you remember it, but there's something on your unit circle that does sine of alpha plus beta. Sine of a plus b would simplify into sine of a, cosine of b. They switch, so this stays the same. Cosine of a, sine of b. You might not remember that, but it's something that we did in pre-calc that you'll see every once in a while again here in calculus. Same argument here. This is not distributed. It's not log times this group. It's log of. So this is of, not mult. You actually can't clean this up. There is no way to simplify that. Argument, same argument here. This is log of, and so you can't distribute the log to both pieces. Now there is a trick with this. This is, again, I'm going to rewrite it as of, not mult. Now, some people might see this and you might be thinking of a multiply thing. There is this multiply thing with log, but it kind of goes the other way. This is legal. So if it was log of a times b, then you could split them up into their own logs, but it doesn't work that way for addition. Again, here, common mistake. People want to kill off this log by dividing by it, by canceling it out via division. It can't. Log cannot be divided because it's not connected by mult. To the cancels log. So like for instance, if I had log base 5 equals, dang it, log base 5 of x equals 9, I would go 5 to the and 5 to get x equals 5 to the 9th. You might remember that from pre-calc days. Okay, reducing errors. Very common because we always want to cancel things out to make stuff look nicer. I get it. But we can only cancel in certain scenarios. We cannot reduce these b's. We can't reduce it because the addition and division, usually they're okay to work together, but you have to make sure that you divide it from everything. This b is underneath both of these, and if you can't divide it by both of them, then you can't reduce. Can only reduce if all terms have the GCF that you're trying to cancel out. So in this case, the b is not in common. Same thing over here. As we look at this one, we can't simplify the 10s. Not everything has a 10. We can't simplify the b's. Not everything has a b. So unfortunately, you can't kill off those pieces. Same as part A, 5A. You can't simplify that for the exact same reasons. Again, how is sine connected to x? How is sine connected to y? It's not mult. If it were mult, then this would be legal, that you could cancel those out, but it's not. It's sine of. So this is an example of, not mult. Same thing here. I can't cancel a natural log with another natural log because this is connected by of, not mult. Of does not get canceled by division. Multiplication does. Look in here. It's starting to sound like a broken record, but it's the same idea. I can't kill this. I can't cancel an A from both of these because that's not even really an A. That A is trapped inside of the sign. So this is sine of 2A together. So I can't just kill that out. So again, this is of, not mult. I mean, you wouldn't cancel square root of 2 over 2, or at least I hope not. That was one of our trig things from last year, one of our perfect square, special right triangle. Sorry, it's a special right triangle. And then also the same thing here. You can't just kill off a squared. You can't square root both of them and get the same answer. I mean, let's quickly come up with an example, and I'll prove it to you. Let's put some numbers in here. Exponents aren't canceled by division. Exponents are not canceled by division. So like, let me show you what I'm talking about here. Let's put some numbers in there. So is 2 squared over 5 squared the same as 2 over 5? No, 2 squared is 4 over, I wonder if I should have done, let me do a better one. Let's do 2 squared over 3 squared. Is that the same as 2 over 3? Well, 2 squared is 4. 3 squared is 9. Is 4 over 9 the same as 2 over 3? No. 4 over 9 is less than halfway, right? That 4.5 is halfway of 9. 2 over 3 is over halfway. Half of 3 is 1.3. This is a number smaller than 0.5. This is a number bigger than 0.5. It just doesn't work. And then the last one that I want to talk about here are the ZPP errors. When I was a student, I remember taking my, I think it was SAT or maybe college entrance exam, one of them. And it was problems like this, and I applied the ZPP everywhere. Now, the ZPP only works if you have two things multiplied together that equal 0. So if A times B equals 0, then either A equals 0 or B equals 0. That makes sense, right? If you're going to get an answer of 0 with multiply, you have to multiply by 0. I mean, think of this. Either A has to be 0 or B has to be 0. If you're adding two numbers, there's lots of numbers that I can add together that give me an answer of 0 without either of them being 0. 7 and -7, for instance. So the ZPP, it's the zero product property, not the zero addition property or something like that. They have to be multiplied together. And then if you go over here, a common mistake is that when you ZPP, remember how this works. If I had, like, let's say x times x minus 2 equals 0, I'm allowed to say x equals 0 and x minus 2 equals 0, and then we would solve and we'd get our two answers. This doesn't work if your equation is equal to something besides 0, because there are lots of numbers that I could multiply together to get 3. I mean, 1 and 3 is obvious, but then what about like 1/2 and 6 or 1/3 and 9, right? There are lots of ways to multiply together and get an answer of 3. There are not lots of ways to multiply together and get an answer of 0. That's why it's called the zero product property. So in this case, it's the zero product property, not the 3 product property or the 7 product property or whatever the case may be. Okay, so hopefully that cleared up some stuff. A nice little review for you about some of our mistakes when it comes to cleaning up algebra stuff.